Okay, Assalamualaikum and good morning. So today we have some lecture for chapter 2, the fundamental equation of compressible fluid flow. And then I think if you read the textbook, everything is actually the introduction from the previous topics. But I would like to share here the idea of the dimensionless parameter in viscous flow. The dimensionless parameter means, I think some of you already learned about the dimensionless parameter. We are using the idea of dimensionless Buckingham pi theorem. So it's Buckingham pi theorem. So means that we try to use the dimensionless. So means one parameter without any units that could give us idea to solve fluid flow. For example, the very common dimensionless parameter in fluid mechanics is Reynolds number. So everybody, I think, in undergraduate, they already know how to calculate the Reynolds number. But when you study in master level, I hope you could have ideas of to use the correct equation for Reynolds number. You know what equation that's suitable on that situation, and what is the physical meaning of Reynolds number, and how to determine or how to achieve that physical meaning. So for example, the Reynolds number here. So normally we are using the idea of Reynolds number is equal to rho Vd over mu, but sometimes we need to use the idea of Reynolds number is equal to rho Vl over mu, and sometimes you need to use the Reynolds number of rho Vrh over mu. So mean Rh here is the hydraulic radius, so normally we are using in open channel. So and then open channel. So and then rho Vl over mu, normally we are using in aerofoil, for example. So and then if we use the rho Vd over mu, so sometimes this is often used in flow in pipe. Okay, so and then you could see here the dimensionless number is actually depends on the situation. So I hope when you do your research, so please choose carefully what parameter that you want to substitute in your dimensionless number. And then every dimensionless has its own physical meaning. So for example, the Reynolds number, the most famous dimensionless parameter, is to show us whether the flow is laminar and turbulent. So means that after certain value of that dimensionless number, so the value is turbulent. So mean that the flow is turbulent. But you must make sure that you know the transition, you know the boundary, the borderline. For example, for flow in pipes, normally we are using more than 4,000, so it is turbulent. And if for aerofoil, if you use rho Vl over mu, so the transition or the boundary between laminar and turbulent is 5 times 10 to the power of 5. So and then if you are using open channel, so they are using around 1,000 or 500. Okay, so means that you need to very particular to use all the dimensionless. So and then in this topic, so I will not showing you the idea of how to solve problems in dimensionless in normal way. So we are now using the idea how to get the dimensionless from the partial derivation, because previously in our chapter 1, so we are looking for Navier-Stokes equation, and you know the Navier-Stokes equation, they have a lot of partial differential form. So and then sometimes we could define what is the dimensionless parameter that could reflect from the situation, from the simplified Navier-Stokes equation. Okay, so dimensionless parameter in viscous flow, since our basic equation of motion are extremely difficult to analyze in general, we should cast them in their most efficient form, thereby increasing the usefulness of whatever solution we find. This is accomplished by non-dimensionalizing the equation and boundary condition. For simplicity, assume constant Cp and Cv approximately true for all gases, and also neglect the second coefficient of viscosity lambda, which is seldom needed. Then our four variable P for pressure, rho, V, and T will depend upon space and time, and 8 parameters that occur in the basic equation of boundary condition. So actually the idea of this idea is we try to neglect the not so very common parameter, because not so very common parameter normally will not affect the system, will not affect the system. Okay, so the four parameter that usually give massive changes in fluid is listed like this, which is the velocity, the pressure, the density, and also the temperature. Okay, so and then in dimensionless parameter, I will summarize this note. So in dimensionless parameter, actually we divide all the units, means all the parameter that influence the system into three major groups. One is called geometry. Okay, so here normally they will call geometry, but here normally people will go for the length. Mean the size of certain object, the size of your object, the size of your focus area, and so on, is one of the main parameter that influence the changes. So mean the geometry, and then the geometry need to be, you need to choose the very influence geometry for that system. So for example, in the first slide, I show you that the Reynolds number has three equation. You may use rho Vd, you may use over mu, you may use rho Vl over mu, and then you may use rho Vrh over mu. So why people change this one? Because people found that their object, okay, is most influenced by this parameter. So it's depend on the situation. So for example, if water flow inside a pipe here, so means that the water flow like this, and then researcher found that the cross-sectional area here is the most influenced parameter. Okay, so that's why they take the diameter here as the most influenced parameter in terms of geometry. So, and then if you have an aerofoil, okay, you have the angle of attack and so on and so forth. So we found that instead of the thickness of the aerofoil, the length of this aerofoil, so mean the span length there is most influenced geometry parameter. So they replace the term D here with the term of L here. So and then for this RH, so RH means hydraulic diameter, hydraulic radius. So hydraulic radius normally used in open channel. So open channel mean we have a conduit like this. So sometimes the shape of the conduit is in rectangular. So for sure in rectangular, there are no radius. So to reflect the importance of the importance of the geometry, they will use the idea of hydraulic radius. So hydraulic radius, the equation is the cross-sectional area divided by the weighted parameter. So I hope in your research later on in your master study, so you may use these dimensionless parameter correctly, because sometimes I found that they take a wrong parameter to make the calculation. Okay, first means that the geometry of that object, and then the second one for sure, because in fluid mechanics, if the fluid is not moving, so the pressure will not occur, the force will not occur. So it's just a fluid static. So it's about for example, the buoyancy. If you have a boat in ocean, for example, so that is about the only the fluid static. So if the boat is start moving, so means that the fluid is actually relatively move or flow pass through the boats. Okay. So and then the second geometry is about the velocity here. So and then normally the velocity will the most famous parameter in fluid mechanics. So you must make sure that to make sure you have a good dimensionless parameter. So please take the velocity is one of the important parameters. And then the third one is the stream properties, mean the properties of the fluid. So we have pressure, we have rho, we have temperature, we have mu, we have another parameter. So normally people will take the density of the fluid is the major concern in doing the dimensionless parameter. So and then sometimes you could use very straightforward. So for example, if you are doing flow in pipe, maybe you could use Reynolds number, or you could use normally we are using a Reynolds number if you are doing flow in pipes. But sometimes you may have difficulties to determine what dimensionless parameter that you need to use, that you could use in your research. Okay, so and then here, for example, another complicated that you will face is sometimes you are dealing with simulation, you are using a lot of Navier-Stokes equation, you have equation which has partial differential. So and then it's maybe you need to do the dimensionless parameter. And then in this topic, I would like to show you how to do the dimensionless, how to get your dimensionless parameter according to your partial differential equation. Okay, normally we need to define the dimensionless variable like this. Okay, so this is fixed actually. It is good for you to remember this one, but or at least you keep these notes for your future use. Okay, so the idea of dimensionless is we try to divide all the current parameter that we have with the reference value. So means that if you divide the value of length with the reference length, mean the unit will be cancelled off. So there are no unit anymore. So now it will become the dimensionless parameter. Okay, normally for example, if we have length of x, so we divide with the reference length L, and then we could get the L x star here. So mean x star now is just a number without any dimension. So and then we have if we have t time here, so we have t times u velocity over L, because you know that we cannot say that okay we could divide the current time with the reference time, so it will show us wrong interpretation, because time is quite very unique parameter. So we not divide just like that. Okay, so we are using this. So this is the pressure, okay, and then this is the density, dynamic viscosity, velocity, and so on. Okay, so normally in exam, I will give you this table to do the dimensionless calculation. Okay, let's say we do the dimensionless for continuity equation. So the idea of continuity equation is discussed in chapter 1. So I think the idea of continuity equation is very simple. We want to prove that the conservation of mass. So mean the mass must be constant, and then the equation of mass is shown like this. So means that mass is equal to rho time volume. So this is the idea of, we know that the density is equal to mass over volume. So if we rearrange this equation, we have mass over volume. So if we rearrange this equation, we will get that the mass is equal to rho times volume. Okay, So and then we could have the idea of okay, this is just the note. I skip this one. Okay. So and then in normal calculation, we have two types of continuity equation. One is about the flow rate, the volume flow rate. So the volume flow rate, the unit is meter cube per second. So and then the equation is A times V. So Q sama dengan A times V, like this one. So and then another continuity equation that you could use in application is the mass flow rate, which is the m dot. It is equal to kilogram per second, and the equation is rho A and V. Okay. Okay, so let's say the continuity equation, okay, given is like this one. Okay, so and then we try to do the dimensionless calculation here to get what kind of dimensionless parameter that we could use in continuity equation. So let's say because we have parameter of density here, we have parameter of t, we have parameter of velocity here, so means that and then we have the parameter of nabla here. So this triangle is called nabla. So and then what we need to do is we need to check our table, and please make sure that we have the dimensionless variable for all the parameter in our equation here. So and then for example for rho, we have rho star, rho over rho naught, T star is Tu over L, and so on and so forth. Okay, so and then, okay, what we need to do is by rearrange this equation, these terms, we need to substitute into the equation. So we need to substitute the rho here. So we change from this term, we change into rho equal rho star rho naught, and so on and so forth. So and then we substitute all the variables into the equation. So we have the del, rho star, rho naught, and so on and so forth, like this one. And then the next step is we try to factorize. So we take out the terms, which is, and then we must make sure that it could reflect or it could have a same arrangement with the previous, with this one. So for example, we have d rho over dt plus divergence of rho v. So we have this one. So we have the del rho star over del t star plus rho star over the, so this is come from this one. So this is the nabla, rho, and v. So we will get the nabla star, rho star, and v star. So and then after this, we could factorize this one because we have the same terms here, rho naught u over L. So but we could bring to the left hand side here, so means that the final equation is like this. So if you have this term, and this term is similar with the previous term, the original equation here. Okay. The original equation here, so means that we could make conclusion that there are no dimensionless parameter could produce from the continuity equation.